Hey guys, Dr. J here, and in this video we are going to introduce remote sensing with application to UAVs. So we're going to talk about the aspects of remote sensing that's related to drones and drone mapping in particular. So what is remote sensing? Remote sensing is the science and art, a little bit, of obtaining information about a surface or an object through analysis of data acquired remotely, so not in contact. So we're talking about satellites, drones, imagery. What can we learn about a material, about an object, about an area based on remote sensing of that object? And so it's anything which is not in direct contact. Specifically, remote sensing today is typically used to refer to either satellite or drone imagery that's been acquired. This could be, for example, a multispectral satellite like Landsat or Sentinel-2 are very common. It could be a radar satellite like SAR. The Sentinel-1 satellite, for example, is a SAR satellite. Or it could be from a drone. So we could have a multispectral, thermal, optical, LiDAR. Those are all remote sensing methods. So what we've been talking about in these videos so far are pretty much all remote sensing methods. We're not going up to something and putting a probe in or taking a direct measurement of the object. We're doing it remotely. And there's many reasons to use remote sensing data. One of the reasons is that we can get a very large view of a very large area. So if we're using satellites, for example, even if we're using drones, we can see more than what we can see just on the ground. And we're able to use different sensors and get information about different bandwidths and frequencies. And we can use even different types of sensors, so optical or multispectral compared to radar, for example. And so this is one reason to use remote sensing data. Another reason is just that we often can't get access to a site on the ground. For example, if we wanted to fly over an area where we didn't have physical access to, we could still do that and get remotely sensed information. This can be, again, at the scale of a whole country. Maybe we want to see what's going on over in some other country, or maybe we want to see what's going on over a large facility where maybe we don't have access to that entire facility. Maybe we've been hired to survey a construction site or a factory, and we can't necessarily get to every specific place, but we can image that area from the air. However, it is important to keep in mind with remote sensing that we're not directly measuring things, right? That's the whole idea, is we're remotely sensing information. And so we need to figure out how to relate the signals of interest or the things that we're interested in to the actual signals that we get. We need some kind of models. We have to make some assumptions in some cases. And we might have very large data sets that we would have to process. We want to be able to ground truth this data. So this is all part of the challenges and the opportunities of remote sensing data. A little bit about the history of remote sensing. So you can see some examples here of early remotely sensed observations, photos from a balloon, first aerial photograph taken from an airplane in Italy. So these are, this was kind of the beginnings, just using cameras. And this use of cameras is, of course, very important from a military perspective. And so military operations in particular, remote sensing sort of came into its own. Thinking about aerial photography for either World War I or World War II, this was where remote sensing really began to be developed. And again, mostly just using optical cameras. Today, we have all sorts of different types of platforms and sensors. So we have satellites, we have aircraft, we have drones, and of course, all these are tied together using GPS often. And so here's just some examples of different sensors that we have. We can even have ground-based remote sensing sensors. So for example, terrestrial LiDAR scanning, TLS, is an example of a remote sensing method, which is actually based on the ground. So all sorts of different platforms, space-based, air-based, and of course, we have our drones. We can see changes through time. So by looking at the same area on the ground through time, we can get information about how things are changing, how developments are happening, how cities are being developed and growing, how we can see changes in forests and plants, and we can see really changes of many different sorts using remote sensing data. We can use this remote sensing data to do catastrophe modeling or natural hazards monitoring. So whether that's landslides or earthquakes or sinkholes or groundwater-related subsidence, we can look at changes through time and monitor those changes and use those changes or use that information to make decisions. Here's an example from INSAR, which is a radar satellite. And this is a case where you can actually take the phase of two different measurements, SAR measurements. You can do interferometry on those measurements, and you can calculate displacements of the ground. And in this case, each one of these fringes, we call these fringes here, where it goes from one color through other colors to that same color again. So blue to yellow and red to blue. That is one fringe. And each of these fringes represents, in this case, I think 5.5 centimeters of displacement. So this was a very large earthquake, magnitude 7 earthquake here, magnitude 6 earthquake here. And the displacements from these earthquakes was probably, looks like almost a meter in some places. So we can calculate ground movements using satellite remote sensing data. We have, generally speaking, two types of sensors, passive and active. And if you've taken a course on remote sensing, then this is going to be mostly review for you. But just wanted to kind of provide this overview in case you haven't had that background. So passive sensors are using radiation from the sun or another external source. Active sensors are generating their own energy. So radar, LiDAR would be active sensors. Multispectral optical cameras would be passive sensors. They're using the sunlight or other light sources to illuminate a surface, and they're just recording that illumination. The sun is the most common illumination source for passive sensors. Agricultural applications, for example, would use optical or multispectral or thermal, and those are all going to be passive. As I mentioned, the radar and LiDAR sensors are going to both be active sensors that are actively transmitting light rays, either in the radar wavelength or in the infrared wavelength. And those are going to be, active sensors, waves that will be transmitted and then reflected back to the sensor. And again, this is for a passive sensor. Energy source, radiation from the source through the atmosphere to the sensor. If we have an active source, that could also be radiation from the source to the target, and then from the target back to the source. Transmission and reception and processing, that's getting the data to your computer, essentially, and then potentially doing some processing on the data, interpretation and analysis, and then using that interpreted data to make some decisions. So this is kind of the general workflow of how we use remote sensing data. And I guess the key that I want to point out just for the purposes of this lecture is that you have some illumination source, either for passive, it's from the sun, for an active, it's from the sensor, and that energy gets transmitted to a target surface and then reflected back to the sensor to be collected as the signal of interest from that target. Let's talk about different types of energy or types of wavelengths of light. So probably many of you have seen a diagram like this before in high school or in college. We have a whole spectrum of electromagnetic radiation, including visible light. So this is where our optical sensors are focused. We also have multispectral sensors, which might be more into the infrared range and do other types of waves. Microwaves and radar waves, those are kind of even longer wavelengths. Radio and broadcast bands, those are even longer wavelengths, even kilometers long wavelengths. And a wavelength, just as a reminder, is the distance between peaks or the distance between troughs in a single wave. So shorter wavelengths tend to have higher energy, are more dangerous. Cosmic rays, gamma rays, X-rays, those are all more dangerous. Shorter wavelengths, more energy. And then longer wavelengths are lower energy, less dangerous to humans, and are useful for making remote sensing measurements. So almost all of our remote sensing technology is based on the optical wavelengths and longer wavelengths. And you can see some examples of what those wavelengths are in nanometers for visible light. And as we get up to radio waves and longer, that's meter to kilometer long wavelengths. Radar and microwaves are going to be kind of in the millimeters to centimeters long wavelengths category. And different wavelengths or frequencies are absorbed or transmitted differently through the atmosphere. So the visible light is obviously one that's transmitted very well. A lot of our shorter wavelengths get blocked by the atmosphere, which is good. That's good for us. And then again, you sort of see there's various areas where more or less of the signal gets transmitted versus blocked. Radio is one that gets transmitted pretty well. And you can see here this area between visible light and microwaves. In this area here is where a lot of our radar wavelength sensors are located. So they will They will specifically put the energy in these specific wavelengths that allow some transmission through the atmosphere. So that's on the transmission side. If we look at the reflectance side, so again, we're transmitting energy to the surface, to a target, and that's getting reflected back. And here's the key piece of information for remote sensing, and that is that different targets reflect different frequencies of light differently. So the example shown here is for plants, different types of plants, or bare soil or water. These are all going to be reflecting different amounts of light in different wavelengths. And so if we look at two different diagrams here, sorry, this one's a little hard to read, but basically these different lines show how much light is reflected, how much energy is reflected in each one of these wavelengths, from 100% reflected to 0%, all absorbed. So growing plants obviously absorb certain wavelengths, blue and red, excuse me, and then green as well, although not as much. Infrared gets reflected back. Near infrared and longer wavelengths get reflected back to the sensor. And this is true with pretty much many different things. So buildings or fields or bare rock, these are all going to have different responses in the frequency domain. So these are frequency domain, meaning what are the different wavelengths of light that are represented there, and how much is getting reflected back at each wavelength. So these different, and this is why multispectral sensors are so powerful, is that you can get the reflectance information at each one of these wavelengths, and you can just tell by looking at these reflectance patterns that it would be pretty easy to distinguish between many of these sources based on how much gets reflected back in each one of these wavelengths. So let's talk about some details, some technical parameters defining a remote sensing measurement. We've got different types of resolution. So if you say, what's the resolution of your measurement, we need to talk about what type of resolution are you talking about? Spatial, spectral, temporal. There are these different types of resolutions. So let's talk about spatial resolution. That is the ability to resolve or separate small details. This you can think about as a pixel size. So this might be two different images here with two different resolutions. One looks blurry, one looks clear. The one that looks clear has a higher resolution. And this is often also related to the size of the image overall. So a MODIS image, for example, might be much larger than a Landsat image. Tens of meters of resolution would be a typical satellite resolution, versus very high resolution satellite data versus drone resolution. So for drones, for UAVs, we're usually talking about centimeters of ground sample distance, pixel size. Again, just some definitions here. Instantaneous field of view is basically the range that the sensor is seeing at a particular moment in time. And so we're able to see more from a sensor which is higher, for example. So if the elevation of the sensor goes up, we're actually able to see more of the ground, but at a lower resolution, right? So lower resolution will be a higher platform, but a larger field of view, and vice versa. So if we decrease our field of view, that means moving closer to the target. That means we're increasing our resolution of that target. Let's talk about spectral resolution. So spectral resolution would be how fine of spectral information you can obtain from a system. And the example shown here is the Landsat example with 7 bands. And just making a plot, you can see these endpoints of these lines are the points where you have spectral information, versus an Aviris sensor, for example, which would be considered a hyperspectral sensor. And here you might have several hundred spectral bands, which have very fine resolution, spectral resolution. Radiometric resolution is the ability to discriminate slight differences in energy. And this is measured in bits. So you can see here, if we have just 1 bit, we can distinguish basically between 2 levels of energy. So that would be a very low radiometric resolution. 11 bits gives us 248 levels. That would be a very high radiometric resolution. So the place where this is going to commonly come up for you all is with our thermal sensors. We want to know how much thermal sensitivity we have, and that's going to allow us to distinguish between various temperature targets, or targets at various temperatures. So if we have very fine radiometric resolution with our thermal cameras, we can distinguish very fine differences between temperatures of different systems or different targets. Let's talk about temporal resolution. Temporal resolution is a measure of how often data are obtained for the same area. We actually will have another video on multitemporal analysis of drone data. But as you can imagine, there are tons of applications for temporal multi-temporal data. So you can see changes in land use or land cover over time. Variation, we've already shown the example of how a city development over time can be seen using remote sensing data. Monitoring of a dynamic event, so tectonic events, floods, hurricanes, volcanoes, earthquakes. These are all things that are happening in time, and we want to be able to monitor them in time and see how things are changing. We want to see how things are changing in time. So this is the importance of temporal resolution.